Hello, you beautiful people. So today it's time for the solution to the last worksheet, worksheet number 4. And we had the topic of changing density in a plug flow reactor. Worksheet 4 was about calculating this plug flow reactor. So we wanted to have a mole flow of component C of 30 kilomoles per hour with a conversion of 80% of component A. We start with a concentration of 20 kilomoles per cubic meter, and yeah, your task was to find out what should be the reaction volume for this task. And we started with a simple one. So we said, okay, we want to have a reaction with a constant density. So this is basically a repetition of what we did in chemical reaction engineering in the bachelor's course. And so this is, hopefully that was an easy one. And let's have a look how we can solve this. So I hope you all found the equation that your residence time is the same as your starting concentration, and then you have to solve the integral from 0 to your conversion. And then 1 over Ra, the reaction rate of component A, times dxa. Oh, this A is ugly, let me draw it new. Okay, and here we had a first order reaction. So first order, this means Ra is the same as K times Ca. And this you can rewrite as, well, as K times Ca0 times 1 minus Xa. Then let's put it here in this equation. Then we have again our integral, then 1 over K times Ca0, 1 minus Xa dxa. Okay, then we can skip the start concentration. This cancels out, then your K is constant. You can write it in front of your integral, and then we just change the minus sign in here so that I can solve it very easily, what I know from my math courses. So we can rewrite this as 1 over K, then integral 1 over Xa, and then it's 1 over Xa minus 1 dxa. Okay, and this, I hope you remember this, or if not, you have to look it up in some integral tables. But this is 1 over K, and then it's ln, and then Xa minus 1, and if you insert your start constant, your start conversion, so this is 0, then you just have minus 1 here below it. And yeah, this you can basically rewrite as minus 1 over K ln, and then you can rearrange the minus here. So this would then be 1 minus Xa. So then we can just use the values that we know. Minus K was given in worksheet 4. This was 1 times our to the minus 1, and then ln, your conversion rate was 80%, so 1 minus 0.8 is 0.2, and so this is smaller than 1. Your logarithm of something smaller than 1 is negative, so minus times minus is plus, so you have a positive residence time. This is quite good, and then you get a value of 1.609 hours. Okay, but actually the question was not the residence time, but the reactor volume. So maybe we can say, okay, this is volume divided by the volume flow, and then you can say my reactor volume is tau times V constant, and this is 1.609 hours times 1.875 cubic meters per hour, and then you end up with a reactor volume of 3.018 cubic meters. Okay, this value here we calculated in the last worksheet, so this was just copy and paste from worksheet 3. From worksheet 3. Okay, that was the easy one, I think. Now it's B. Consider a reaction with a change in density with an epsilon of 0.5. Calculate the correct reaction volume V epsilon by solving the integral of equation 8. A table of integrals can be found here. So basically you had a link where you found a lot of integrals, and the one that you need for the task given here I put here in the red box. So again we start with our equation. Let's go back to red. We start with our equation. The residence time is CA0 integral 1xa 1 over RA dxa. Again, RA is K times CA, and now CA depends on your conversion rate, but also on your fractional change in density. So CA is the same as CA0, your inlet concentration, times 1 minus XA over 1 plus epsilon XA. Okay, now we have to insert it here. Then again CA0 cancels out. Oh, I can write it here, no problem. So it's CA0, then you have integral, and then below your under the line you have K times CA0 times 1 minus XA, and above you have 1 plus epsilon XA. And this you have to integrate with respect to XA. Okay, and now you just have to compare. So you can say, okay, CA, this cancels out, K is a constant, you put it in front of your integral. But what you have to do now is you have to compare it. Okay, let's start. Your A is epsilon. Just by comparing the above integral in the red box and by our equation that we have here. So then your B is 1. Then you go on, C is minus 1, and your D is 1. Okay, and now here's the solution of your integral. This means you can just put it in here. So tau is 1 over K, and then you just have to write it here just by comparing. So A is epsilon, so then you have epsilon XA over C. C is minus 1. Okay, then you have plus B times C is minus 1 minus A times D. A is epsilon, D is 1, so minus epsilon over minus 1 squared, so this will become 1, so this will become positive. And then you have your ln from minus x plus 1. And we know our integration limits, so this is xa and this is 0. Okay, if you put in 0 for your lower bound of your integral, then you will find, okay, the first term cancels out, because here you have xa. If xa is 0, then the first term cancels out. If you put it here, then you have a logarithm or natural logarithm from 1, and ln 1 is 0, so the terms for your conversion rate of 0, they totally cancel out. So you just have to, or you can write tau is equal to 1 over k, and then it's, or we can put the minus sign in front. That's what I did in my solution, so it's 1 over k, and then you have epsilon times xa plus, so again here the minus is here in front of the brackets, plus 1 plus epsilon, one plus epsilon, and then you have ln from 1 minus x. And then you can close the big brackets. Okay. Then, whoops, no. Beibehalten. So just a short control. If we say what happens to this equation if we say our epsilon should become 0, then you have your residence time is minus 1 over k. Then the first term cancels out. Then you just have 1 plus 0 is 1, and then you have ln from 1 minus xa. I forgot the a's on top here, so a. And if you compare this to what we found for the case of constant density, whoops, then this is what we found for the first case. Okay, so hopefully this formula is correct, and then we can go for the calculation. So tau is equal to minus 1 over k. What was it? Epsilon times xa plus 1 plus epsilon ln 1 minus xa. Okay, this is minus 1 over 1, and then its epsilon is 0.5, the conversion is 0.8, plus 1.5 times ln 0.2, and then I end up with a residence time of 2.0142 hours. And again, we want to know our reaction volume. So the reaction volume is just the volume flow times the residence time, and this is 1.875 cubic meters per hour times 2.0142 hours, and then you have 3.777 cubic meters. Okay, and then unfortunately I did a very stupid mistake on the email test. I asked you to calculate, okay, the volume of worksheet 3 divided by this newly calculated volume with the change in density. So in worksheet 3 we had the volume for the CSTR. We had a volume of 10.5 cubic meters, and now it's 3.777 cubic meters, and then you end up with a ratio of 2.78. So if you decide to go for CSTR, then you need a reaction volume that is nearly 2.8 times bigger than the one for a plug flow reactor. But let's take an Emil. I put the wrong solution there, so there I put V epsilon divided by V3, and this should be something like 0.36. So sorry about that. Okay, the part D was about the Euler scheme. I just copied you a part of my code here, so this is the important ones. How did I do this? So we want to know when is a conversion of 80% reached. So this time I solved it with the while function. So I'm always checking the maximum conversion, and if this is below my target conversion of 80%, then this loop is done again and again. And if the conversion rate is bigger than 80%, then it will stop, and we know our volume in the end. Okay, so basically it's you have to calculate your concentration by your mole flows. With the concentration you can calculate your reaction rate. Then you can say, okay, the change in mole flow is the reaction rate times the volume of your very small slide. And then if you know your delta n, you can say, okay, what is my change in the mole flows? So component A is reduced. That's why you have here a minus. Component B is produced, but it's just the half of it. And component C, this is the plus here. And then you can say, okay, what is my conversion? The conversion is just the initial mole flow minus the actual mole flow divided by the initial mole flow. Then you can correct your volume flow. So it's in the first or in the beginning, somehow I got mixed up with the volume of the reactor and the volume flow through the reactor. So that was a little bit tricky to find good expressions for it. So this is the volume flow that is corrected. Then if you're interested in it, then you can also calculate your residence time, your residence time, and here you just increase your volume, that you know, okay, my total reactor volume is increasing with every loop here. So, and basically that's it. And if you do it like this, then you end up with a plot that should look like this. So here is 80% conversion of our component A. And here you can see how component B and C are produced, and yeah, here you can see the mole flows. To check if you got your simulation right, I asked you for the concentration at a volume, so this is inside of your reactor. And yes, so I found out that the concentration A at 2 cubic meters should be something like 6.17 kilomole per cubic meters. So this I plotted here. And again, if you look here, you can see that our reaction volume is in the range of 3.7 something, and if you look here, this fits quite well to what we got by the analytical solution by solving the integral. Okay, basically that was just what I wanted to show you. You can decide if you want to go for the numerical solution or if you want to go for the analytical solution by looking up in the integral tables. So basically it's up to you. If you don't have MATLAB at hand or Excel or something else, then I would recommend strongly to go for the analytical solution. Okay, thank you for listening, and bye bye.